Okay, hello. This is another good problem. It talks about higher dimensional spaces and just the different ways to describe them. And again, these first few problems are sort of a lot, but they're important because, in my opinion, these are the main things that are confusing throughout the term and, in fact, throughout all your future courses. So here's the last one. Describing spaces, describing subsets of the plane, of space, of anything. And there are just several ways to do it, and so we're just going to point out these different ways. And then also point out that sometimes it's completely impossible to go from one description to another. Other times, we can do it. And in my experience, in classes in the future, professors sometimes forget that it's impossible in general, and they pretend like it's very easy in the particular example they're looking at. For example, like the circle, it happens to be easy to go from one to the other. But in general, it's impossible. So, and for the circle, it is difficult the first time you're seeing it, but professors in the future or you in the future might forget and forget how difficult it was the first time. So actually, we're just going to take the circle and use it for most of these examples. So, okay, so the units, you can of course take different examples, but this is a good one. The unit circle is the preimage of the point 0 under the map given by this formula. So it takes two real numbers and spits out a real number. For example, it takes 5, 2, and spits out the number 25 plus 4 minus 1 equals 28. Right, so this is just a map. It takes two numbers and spits out 1. But the preimage of 0 is the circle. So in particular, the point 5, 2 is not on the circle because it spits out 28. So 5, 2 is in the preimage of 28. It's not in the preimage of 0. So the preimage is all the points that spit out 0. And in this case, they have a geometrical shape. And that shape is the circle. In fact, the unit circle, because of how we defined our map with a 1 that becomes the radius. Okay, but the circle is also the image of a map. So before it was a preimage, now it's the image. And so here's a map. Here's the coordinate I chose for my input space. And I didn't even write down coordinates for my output space. I could write y1, y2, or x1, x2 or something, but you don't need to, always. When t varies between 0 and 2 pi, this map spits out points in the plane, and it spits out exactly the unit circle. Those are the images now in the output space. Yeah, and note that this is not a graph, right? So in fact, that's the next one. So now a graph is is also the image. It's giving their space as the image of a map. But the graph is a little different. It's more special, and in fact, the circle cannot be written as a graph. Only pieces of the circle can be written as a graph, because graphs are more special. Okay, and yet it's weird to me that graphs are basically the only thing you see in your usual calculus and multivariable calculus courses. I don't think that's a good idea at all, because then you're going to be confused in the future. Graphs are special. They do not work. They do not handle the cases we need. In fact, they do not handle the circle. Okay, so, but you can give the top half of the circle as a graph, so that's what I did. So here's my map. It takes a real number and spits out another real number. So the graph is going to be inside of the input and output space. This is just this is like a cross or a times symbol. And when we do it to sets, what we mean is sort of create a bigger space out of those sets by just taking tuples of points, one from the first set and one from the second set. And I think it's intuitively clear, and that's all that really matters. And so if we just restrict this map to be between -1 and 1, by the way, that can be written, sometimes people write it like this as a subset of the real line. This notation here means all the points between -1 and 1. So like another notation would be like -1 less than or equal to x less than or equal to 1. It would be all the points x that satisfy both these two inequalities. And these are just different notations that are potentially confusing, in my opinion. Okay, so I just used words when t varies between -1 and 1 instead of using symbols like this. Okay. Okay, now here's another one, the sample of points. So what do we do? The preimage of a map. Okay, that's sort of like the equation of a circle. The image of a map. This is sometimes called the parametrization of a circle. The graph of a map, it's sort of a special case of that only works sometimes, but when it does work, it's nice. So we couldn't do the circle, but we could do pieces of the circle. And now D, a sample of points. So this is actually one that would come up in reality, because when you're taking measurements, you're performing experiments. You'd have a finite amount of experiments, and that means you have a finite amount of points. And those points are usually in some r to the n. For example, if you're looking at house prices, you might have the square footage of the house, the xy coordinates of the house, like longitude, latitude coordinates of the house. You might, like where, essentially where the house is located. That already is 3 numbers. You might also have the number of bedrooms. That's a 4th number. So each house gives you 4 numbers. So if you look at 100 houses, that means 100 numbers. And they're arranged in R4, and you can look at their geometry. Anyway, so a sample of points. Let's look at a circle. We can try to encode the unit circle by a sample of points. And so I just started writing down some points. The easiest ones were these ones. Then it got a little harder. I had to remember my unit circle. And then I decided, okay, I can make up some more ridiculous points by doing that. And actually, if we use that rational map, what is it? 2t over 1 plus t squared, comma, 1 minus t squared over 1 plus t squared. We can plug in any rational number, like even t equals 117/15, and then plug that in, and we're going to get a point on this circle. So actually, this map, this parametrization, is a nice way to generate points if we didn't have them from some experiment, but we wanted to generate them. And let me just take a moment to think about these things. The unit circle is so important. And it's worthwhile to just remember a few points. Here's the 1/2, and here's 1/2. And those points are, so this point is 1/2 x coordinate. And then just memorize √3/2. You can check it, square both of these, and add them up. You'll get 1. Here the height is 1/2, so this point has height 1/2. What's its x coordinate? Well, √3/2. And then the point that's sort of symmetric, it's a angle pi/4. This point is √2/2, √2/2. And you can always check, you just kind of write down a guess, and then check by squaring, and adding, and in fact you get 1. And so that's how you check that you remembered it correctly. And then the other points are just flip these around. Like down here, there's obviously a point that has positive x coordinate and negative y coordinate. And so that's how you sort of get all these other points on the unit circle. Okay, this one, a vector field on the plane. So describe a higher dimensional space by a vector field. So in fact, vector fields only describe curves. They don't describe surfaces or higher dimensions like that. So this problem is already limited. It sort of doesn't make sense. If you tried to describe, well, Anyway, it's harder, but I wanted to point it out. So what's the idea? So a vector field attaches a vector at every point. So this is what you think. You think at every point there's a little vector attached. Like we're going to see visualizations in class. And so here's this vector field. Oh yeah, so because it assigns or attaches a vector to every point, it's really a map. Everything is maps. So this is a map from the plane to the plane because vectors have two components. And so this is just another way to visualize maps from R2 to R2. And it's very different. And so how does this describe the unit circle? Well, for this very special map, it looks like this. It looks all curvy and windy. And in fact, the unit circle perfectly fits. But what do I mean by fits? It means that at every point on the circle, the arrow, the vector field arrow, is tangent to the circle. And so if I had a different vector field, like something like that looks like this, then to be tangent, I have to sort of, this curve follows the vector field at every point. You can't go like this, okay? You can't have a curve that does that because right here, it's not tangent to the vector field. So the curves that are tangent to the vector field at every point, those are called integral curves of the vector field. So intuitively, this is clear from the drawing. And we're going to talk about it later, so I'm just wanting to throw this picture at you. Okay, so the circle works for this specific vector field, but not for other ones. Okay, and lastly, a system of inequalities. Okay, so this one I chose to go a little bit away from the circle, and I said, okay, the unit ball is the interior of the unit circle, and it's given by the inequality here. The sum of squares is less than or equal to 1. The left half of the unit ball is given by two inequalities. The sum of squares is less than or equal to 1, as before, and then the first coordinate is less than or equal to 0. And now you have the left half of the unit ball. The unit circle is also given by inequalities because x1 squared plus x2 squared equals 1 is equivalent to requiring that x1 squared plus x2 squared be less than or equal to 1 and x1 squared plus x2 squared be greater than or equal to 1. So this is a system of two inequalities, and this is one equality. And so inequalities contain equalities as a special case, and so inequalities are way harder. They have way more things. You can describe way more geometry by inequalities, and because of that, they're way harder. Okay. Is there anything else I want to say about that? I mean, I think that seems to be it. So that was many different ways to describe geometric objects, and it's good to just point them out, and then you sort of know where you are when you're trying to read a problem and understand, or you're trying to think about your experiment and try to understand how to analyze your experiment.